Welcome and good afternoon. This is Understanding, Using and Improving State Generator. My name is Johannes and I first have some questions for you. The first one, who here has been using at least C++20 in some kind of project already? 20? Okay, it's quite some people at 23. Okay, has done something in any way with coroutines? It's getting less. And did something with coroutines where you actually did not just use a library but poked into the details and the internals of it? Okay, that's nice. I think, at least I hope, I have something for everyone. First, a quick introduction about myself. I've been programming in C++ since 2017 roughly. It's getting more and more serious. I'm currently enrolled as a PhD student in Freiburg in southern Germany. Recently, we have founded a company called Cleverize, which tries to give commercial support for our open source RDF and SPARQL engine. So we're building a system that is a kind of a database system which can deal with large data sets. And of course, it's written in modern C++. This is the first time that I'm attending and or speaking a C++ conference. So if you have something to say to me, to give feedback after the talk, be honest, be nice. And here you have my handles if there's something that you want to get in touch with me about. So we'll start with a simple example. This is C++23. Look at the first thing, this Fibonacci gen. The first thing you should see is in line 6. There's this co-yield keyword from C++20. And what this thing does, it produces the Fibonacci sequence. As you read it, you have nice code. And each time, what semantically happens, that you reach this line 6 in this while loop, basically you say, this current value of j is the next value that I'm going to produce to the outside. And if you say, then in the lower part, in the main function, we can call this Fibonacci gen, and it gives us something that we can just use as a range. So we can, in particularly here, use it with all the C++20 range facilities. Here we pipe it into take the first 10 numbers, because if you noticed, our generator is infinite, and then we print them. Now the question is, we see an example. What is this state generator thing? This is what the standard says. A state generator generates a sequence of elements by repeatedly resuming the coroutine from which it was returned. And now the part which we also saw, each time a co-yield statement is evaluated, here in line 6, the coroutine produces one element of the sequence. And I also did some thinking about what is the generator, what is its nature, because we want to understand some construct before we can answer the question, should I use it and what should I use it for? So first of all, it is convenient. You don't have to write this manual iterator, boilerplate type of thing with various type defs and methods, but you just do your synchronous workflow, and each time you have a new value, you do co-yield. Then more technically, it gives you something that is a std range's input range, so you can use it with the range facilities, but as it's an input range, but none of the more strict range concepts, you can iterate it over it strictly sequentially is the word, from begin to end, and also only exactly once. So in particularly, even calling begin twice on a generator is undefined behavior. And technically it's something with coroutines, so it's built on using C++20 coroutines. And in C++23, it is a library type, so if you have C++20, you can use something like this using your own library, or using a third-party library, and in C++20, you can just pull it from the standard library via a simple include. And now this last point is something that we will dive on in the next slide a little bit more. State generator, like in principle all coroutines, is type erased, and this will have some implications on various levels, which we'll see. If you look at this example here, you see what I mean by type erased. We have two generators, one in line on the first line. This is exactly the same as before, and then on line 5. And what the important thing is, They do something different. They have different bodies. They have completely different logic. The one yields the Fibonacci numbers. The other one just yields the number 42 and then is finished. But they both, if you evaluate them, they both have the same type as the generator. So if you look at this function at line 9, I can, at runtime, choose one or the other, although they have internally completely different logic and code that they have to run. So that is the nature of something polymorphic or type erased. The next thing I'm going to do is to quickly show you the interface and all the details, how you can use the C++23 std generator. This here is the template interface. You see 3 template arguments called ref, v, and allocator. And the most typical case is that you only specify the first one of them. If you leave the allocator at the default, we'll talk about this later. You only specify the first argument, which is here called ref, and then the rest is inferred by it. In particularly, the generator is a range, and ranges, in particular, their iterators, they have a value type and a reference type, and all those things are then inferred from this argument according to the following table by example. So the last 3 lines are not really unexpected. So if you specify a reference as the template argument, as a single template argument, then the reference type that your iterators will yield is exactly what you specified, and the value type is the thing that you get if you remove basically all the qualifiers from it. A little bit interesting is the first line. If you only say specify an object type there, if you say generator of size t or generator of string, then your reference type will be an R-value reference. So you will get implicitly, if you iterate over it, you will get R-value references which you can then move on. We'll see an implication of this on one of the next slides. So this was the typical case. Then there's a little bit a more atypical case, or let's say a little bit rarer. That is then if you specify both of them, so the arguments ref and v. And if you specify both of them, then it's just the argument, the ref argument is the reference type, and the v becomes the value type just as you have written them. And a typical use case for this is if you have some kind of range or some kind of scenario where you don't have an actual reference as by the standard concept of a reference as your logical reference type, so the so-called proxy reference. Where, for example, there's this std vector bool specialization since forever, which has certain proxy references that index particular bits. Or here, if you think of something like a zip view in C++20, there your value type is a tuple, but your reference type is a tuple of references. So here, if I have an example where my reference is a tuple of a reference to a string and a reference to an int vector, and my value type is then a tuple of the string and the vector. But that is, you need it when you need it. Yeah. Now a small thing that is unexpected, because you always find a little bit unexpected things in C++20. This example here, it looks reasonable, looks like reasonable code. I have a std generator of type string, yield type string. I create a string, I yield the string. What will now happen is that this line 4 creates a copy. And the reason is that if you remember, if I only specify std string as this argument, then the reference type will be an R-value reference. So to yield on the outside, I need an R-value reference. But here, I yield an L-value reference. So this is something that should be clear, that something should have to happen here. And there's 2 cases. So we have the scenario. Our generator needs an R-value reference. We yield an L-value reference. And then the yielded value is copied. This is something that is not inherently automatic. It's just it's explicitly mandated by the standard. What happened here? The alternative semantic, which you could argue would also be possible, is just that it does not compile, and you would have to explicitly state the copy to be explicit. But it has to be somewhere. And one thing I found, this is explicitly in the standard, but probably I should to write to cppreference.com, because there, at the time I checked last, it was not written, but it's probably something that people should know, because if you use C++, you want to know when you silently copy possibly expensive to copy types. So to summarize these value type categories, I've here some things. Give you some time a look at them. And you can tell me some of them are, let's say, fine in the general level, and some of them have the one or the other flaw. What's the seconds? Does someone have an idea about which of them I could complain? Yes?
Giving a mutable reference to a constant.
Yeah, G4, the thing, G4 is giving a mutable reference to a constant, so it's giving a constant to the mutable reference, I would say, and this just does not compile. It cannot compile because you're giving to something const to something that needs an L value reference. So number 4 is just does not compile, and then G1 and G2, those compile, those do semantically probably what you expect, but they have the silent copy and in G1 with the additional thing that you implicitly have to know that there's an R value reference involved in the example G2 in line 6. At least you see the R value reference visibly. So that was the solution which we just talked about. The last template argument that the generator has is an allocator. And what you can, even if you haven't heard about coroutines at all, what you can deduce is if it has an allocator, it probably allocates memory. And in general, all coroutines need to allocate. We'll go into detail a little bit later. And as all C++ mechanisms, or mostly containers that need to allocate, it defaults to a std allocator. But you can specify your own allocator. For example, most people do this for increased performance. If you know what your allocation pattern is, or if you have a real-time scenario where you need to allocate all memory up front because you cannot allocate at runtime because of real-time behavior. And in this example here, you can also use it to poke into this machinery to say, okay, this generator somewhere needs to allocate. I want to know when and how much. There is a logging allocator, and we see, I tried this out on various compilers, and the simple generator that just yields 2 numbers and otherwise does nothing, on GCC allocates 96 bytes and 64 bytes on client 19. And here already we have to get in, without knowing anything, the idea that there's some overhead involved here because, okay, I'm yielding 2 numbers and then I'm done, but I need 96 bytes. This might be something heavy. The last thing that you can just do with the generator is a special yielding tag type, let's call it, is called std ranges elements off. You see this example taken here. We have a tree, and a standard tree has a value at the root node or at the node, and then optionally, if it's not a leaf, it has possibly a left and a right child. And if I now iterate in order over a tree, I first get everything from the left, then the middle element, and then everything from the right. And now what here, this co-yield ranges elements off in line 13 and 18 does, that is, it yields recursively, yields all the elements of the range there. So it is semantically roughly efficient, equivalent, to a for loop that there says, for each element in left traverse in order, for example, yield that element. And the reason why that is there is that it's a little bit more efficient if you have deep recursion, because then when you need to get the next value, the generator does not have to first go down all the recursive stacks where you currently are in the range that you are recursively yielding, but it can basically jump directly to your inner level. But that's something that you can look up in detail more yourself there. The CPP reference, for example, explains in very nicely how internally this is done. Now we are C++ programmers. We have seen about a new feature, at least new from a newer standard, or maybe new for us. We see, can we use it? And there's two things. The one thing is, does it solve the problem I'm trying to solve semantically? And the other thing is, what is the performance of this thing? Can I use it in performance critical code, in tight loops, or maybe not? And coroutines are also somewhat in some circles a little bit mythical in that many people talk about them, have some preconceptions, but leave their hands off them. And so you get some discussions with some trusted members who talk here. For example, that's from a recent blog post. There's a strong take. Atrocious, I think, is in the English language a strong word. And then this was commented. I don't know here who listens to CPPcast. Could consider it as every 2 weeks. It's always interesting topics. So, but then at least those quotes are new to you. You know the people, you've heard them, so you can imagine their voices. And then yeah. So what are we going to do? There seems to be some discussion. Everybody seems to have an opinion, and Timur tells us we should probably measure, so that's what we're going to do. What I did was I compared this Fibonacci case as some case. If you imagine the Fibonacci sequence is cheap to compute. You have two integers, you have some additions, you have some swapping between them, but it's nothing that is compute, which can be, if you do it directly somewhere, it can be really, really fast. So if we measure something like this, then we get a good idea of the overhead of the iteration mechanism that we're using. And to compare it, I have used as the generator here in line 2 that we have seen on a previous slide. Then in line 5, this is a struct that has a function next that gives you the next Fibonacci number. And it is, I called it inlineable because it's completely defined in the header. The compilers can see through it and can optimize it perfectly. In line 14, I have the same thing, but I've hidden the next function basically in a CPP file in implementation, which the compiler couldn't see. So I also did, of course, the no LTO or things. And then in line 20, what this is, I did the same thing, but that time I hid the next function behind a virtual function call through a pointer to base class. Because those are some of the mechanisms that you could alternatively use to get values from something like directly or also indirectly in a context. And then what I did is benchmark. I used Google Benchmark on a fairly recent processor. And what I did was important. I forced, after each element, I forced a memory barrier. If you know Google Benchmark, there's this do not optimize. So I forced the compiler to use every size t that was yielded as a single instruction. So none of them was allowed to use, for example, vectorization. But still, you see, basically, and on both compilers, there's two classes, so two types of behaviors here. There's the indirect behavior. Basically, you see the non-inlineable and the virtual function, and apparently also the generator. Those have this characteristic that it obviously costs to have some indirection via 1 or 2 hops via a function call, which you cannot know at compile time. And then the inlineable thing is significantly faster. One thing I need to point out here is that the generator, the compiler was able to see it. I defined the generator in the header, but it did not. So the generator, although the compiler completely did see it, behaved like those indirect mechanisms. And also something else, which is something for another talk, for some reason here, Clang is significantly faster, but also not only in the new fancy features, but also in the standard features that have been there forever. But that is something for another talk. So we saw the generator behaves from our measurements like as it has always some indirection, and the compiler does not optimize it well, even if it sees it. In particular, the generator, as we saw, it has to allocate memory, and this always already gives us a hint. Where there's an allocation, there is an indirection. Because if you allocate memory, then every access to this allocated memory goes via some pointer which you first have to dereference. That is, I would say, universally true. And where there's indirection, it is harder for the compiler to inline things because it has to see, oh, there's this indirection, but I know where I'm going to jump to because I can infer it from things I know. That makes it at least harder. So I didn't say it avoids it, but it makes it harder. And in this case, for a generator, obviously it did not do it. And this introduces some overhead. The question is now, we have some overhead. Is that a problem for us or not? Because overheads can be, for example, negligible if anything I'm doing inside and outside the generator is large, is expensive. If I'm reading memory from a file or from a network sockets where I have to wait for milliseconds until something happens, then if there are 10 cycles or 2 nanoseconds overhead, nobody will care. In other cases, if I have a tight loop where I'm managing, where I say I want my algorithm to be vectorized, to be as fast as possible, because I'm only doing very cheap things with trivial types, but I want to have billions per second, then this might as well be, the overhead might be significant, and then you might come to the conclusion, it's unacceptable for me to use this feature here. And the third point, I called it unavoidable, and that is interesting, because we saw the generator behaves like other mechanisms that are indirect, but sometimes you need an indirection. For example, if you need type erasure because something has to be linked in at runtime or has to be decided on at runtime which thing to use, or sometimes you need indirection to keep your compile times at bay. And then if this overhead is unavoidable, then according at least to this initial benchmark, we might as well use the generator for the task because it's then not additionally slower than the alternatives we can use in that case. Now this is something that is important for the hot tight loop case. So Halo is the short version of heap allocation elision optimization. So the compiler is allowed to remove heap allocations if it can basically prove, okay, I have a nested scope here. On all paths I see, I will allocate this here. I will, in any cases, deallocate it before I leave the scope. Then I might as well, I know what I'm putting there, then I might as well put it on the stack and then probably elide it if I see that I can optimize an inline code. And this is allowed. It's also allowed for coroutines, because oftentimes we use our generator exactly in one function and then we are done. This is a case where, in principle, our allocations never leak out. So it is possible, it is allowed, but currently in practice, I could not make a current GCC or Clang use it. So for GCC, as far as I'm informed, it did never do this until now. And you see this is blue. There's a link in the slide. I'm not going to click it now. In Clang, there is some optimization tasks that does heap allocation elision. And at some point in the past, there were versions where heap allocations elision were elided for coroutines, at least for simple cases, but like this. But in the meantime, currently, this relatively reliably never happens. And then there's the long discussions because you take something away from people and they will complain, of course. But you can follow this. I think currently they're discussing whether coroutines, in particular generators, are a special case there where you should do this more aggressively because people expect them to be elided. Because for your std vector, you say, okay, this has always allocated. I know this, but these coroutine things, why does this allocate? I have a nested generator here, but that is something for the compiler vendors. The last point here is important. Everything I just said is not special for std generator. All these allocations, indirection, less inlining goes for every indirect mechanism like type erasure. So for example, if you use something type erased like std function or also a std unique pointer in a case where you have a virtual base class, there you always have this pattern. I typically have an allocation, and then all this goes and I get exactly the same characteristics, which then also our measurements from the table on the previous slide do not contradict this analysis. So at the end of the first part here, from what we know, we have given std generator just out of the box. It's in our standard library. We don't have to do anything, but just plug it out and use it. When can we use it? Click here. The first thing, it has overhead. You have to decide, can you afford the overhead? I can tell something about what we do. We use C++20 with generators in our code base. So we have a third-party library, which we slightly adopted. And we use it to yield large blocks. We're building a database system, and if you've learned in database classes, you have some operations like filters, like joins, the basic operations, grouping. And at runtime, you get a query, and the query has to be mapped to a tree of such operations, but you only know this at runtime, so we stick them together, so you have some kind of indirection type erasure anyway, and then we use generators to basically say I have an operation that streams its result out in large blocks, and there the blocks are large enough such that the convenience is nice, but the overhead is a non-issue there. That is a second point, is a variation of this. You need for some reason type erasure because either you can only have something at runtime or also to keep compile times at bay. Because I don't know if you've seen, if you have like very deeply nested templates, so like deeply piped, for example, ranges, so join view, filter view, transform view of everything, or also this might happen with deeply nested senders and receivers if you're on the really bleeding edge of the standard. Then at some times your template instantiations and your subsequent compilation times, if you do something bad, they might go exponentially up. I changed something from something type erased in an expression library to something not type erased. And if I hadn't stopped it after some time, I think it would still be compiling. So for type erasure, there's excellent talks, for example, by Klaus Igelberger about how to do it and also about the philosophy when and why you would need this. The last point, or the next point here is, when can you use it given your code maintainability? Because oftentimes you're in the scenario that writing a generator, especially for complex control structures, is convenient. It's relatively easy to write, and it's easy to read and to reason about. If you write the equivalent thing with manual iterators, then it becomes much, much more boilerplatey. And then if you say, I can afford the performance overhead, but therefore I get more maintainability because my code is easier to reason about because I have my continuous synchronous control flow inside my coroutine, and I know what this thing does just by looking at it in a single go. But then also, if that's not the case, if you have something simpler, some simpler mechanism, probably you should use that. Maybe we have this proposed idiom which says no raw loops because many loops can be an algorithm. Maybe we get the next thing that is no raw generators because many things can be done by piping in the, by stitching together something we have in the standard library with stud ranges and stud views, because in every standard we're getting more and more of them. But there still remain cases where it's complicated, especially what is nice. Sometimes you have those corner cases where you say, oh, filter view is broken in this cases, or there's this edge case for this filter which does not work, or this thing here needs to be copyable, but I can't make my thing copyable. And then it can also be nice because in the generator you have the exact control over what you're doing. So always make the trade-off. What is the right tool for the job, as you always should. Now, we have talked, the first half of this talk, about generator as it is, as just the natural way to use it. And we've seen it has some overhead, so now the question is, can we do something about this? And an obvious idea, obvious as it came also up in many talks the last 3 days, was okay, I have an overhead. If I'm yielding just integers, numeric values, then I might not yield just one of them and have the overhead per element, but I just batch some of them into a group and then yield the whole batch at once, and thus ideally only having the overhead per batch and thus mitigating it and letting it disappear. So the example on the left, it is not complicated, but it is boilerplatey. We have a buffer, we reserve the buffer, then we do our Fibonacci thing, which we've always done, but we do not immediately yield. But in line 8, we push it into the buffer. And if the buffer is full, then we yield the whole buffer at once, clear it, and start over again. Then, of course, we have now not a generator of single numbers, but a generator of batches. So when consuming, we also have basically two options or variations of them. Either we write a nested for loop, or we use something like join view. There were several talks that talked about that. Okay, join view has some inherent also overhead, but let's say, in this case, in my measurements, we're in that realm where the overhead of the join view is not that bad because the overhead of the coroutine always wins it. So we are always in the ultra tight scenario. For numeric algorithms with integers, you probably should never use it, but we can see how far we can mitigate it. So this is the thing, and the nice thing about this is it helps. So the batching, you see this, the first 4 lines are exactly the table you saw before, but the last 2 are new. And you see for both compilers, you get better performance. Although you have this indirection there, you get much better performance for the indirect cases than yielding single integers at once. So that is a nice thing. The not so nice thing is that here, if you look at the left, half of our code is boilerplate because lines 2 and 3 are only concerned with the buffers, and line 9 through 11, they are also purely boilerplate and have nothing to do with our actual, in this case, Fibonacci logic. Now, what can we do to separate our business logic from the overhead of the iteration mechanism? So the first thing, which is simple, is we say, okay, I have this agnostic code that does not depend on my actual logic, and I just write me a macro for it. And if you see, the question is, does this have to be a macro? Unfortunately, it does, because inside my logic in line 4, I have this coyield keyword, and this coyield keyword, same as a return statement or something, that has to be in the same function. I cannot do this like yield outer also. Yield from the coroutine from which I was called, that is not a thing. So I have to do a macro here. But then in line 16, I just do my co-yield batch macro. And also I have a version where the line 10s and 11, like the set up the buffer, can also be, you can also mitigate this by adding another macro. And then at least you have something that works, that is nice, but it uses a macro. Okay, I have to repeat the question. So the thing is, I'm yielding a reference here because I'm a generator of a const vector reference. Where does that live? And the short answer is the coroutines are specified in a way that it does the right thing. Basically, if you have in this co-yield statement, if you have a reference there, even if it was a temporary, then this would live at least until maybe this co-yield would suspend my coroutine, pass control somewhere completely else, but it's guaranteed to live until I actually come back and in the coroutine resume past line 4. That is the theoretical answer. The standard does the right thing. The practical answer was I found when I first started using this in some scenarios for some special types of classes, I think it was aggregates that contained types that are not trivial, so basically an array of string that you yield as a temporary, that GCC had a bug where you had then lifetime issues, but that was a bug in GCC and not a specification problem. Yes, but that's important. You have to check if you're first in here for what is the lifetime characteristics in these control flow mechanisms. Yes?
The microphones. The performance metrics, are those for an optimized build or an unoptimized build?
So this is an optimized build. It was a fairly recent machine, recent compilers, 03 settings. Yes, but as I said, the thing I did not allow was basically completely get rid of the thing and optimize everything. So as I said, I forced the compiler arbitrarily to actually consume each value. So you could do this by writing each value to a volatile thing, or Google Benchmark has something internally. But other than that, it was optimized. Yeah. So, now this here, the idea is, okay, we had the batching mixed with the Fibonacci sequence. We removed it somewhat with a macro, but can we hide it completely? Basically, we have this generator. This generator has, without having looked at it, it has some internal, quite complicated structure. Can't we also add the batching in there? Such that this example is exactly the sample from the first slide. Basically, the only thing that is different, that in line 5, it does not say the generator, it says batched generator. That's the difference. And the assumption is I've implemented the machinery of this batch generator in a way that this co-yield in line 12 actually does not immediately yield the value, but stores it in a buffer until it's full. Now, what I don't have the time for is give you the complete introduction of all the internals of coroutines, because that is like a half-a-day class. But what we can do is human pattern matching. I point you to the parts that are relevant and interesting, and we can get an idea of what to do there. So this is a greatly simplified and also with many things omitted so-called promise type for a generator. And the promise type has two natures. The one is it specifies the behavior. So in the promise type, you configure basically what happens at co-yield or at the beginning or at the end of the coroutine. And the other thing is it is an object to which everybody has access to. So the inside of the coroutine as well as the outside, in our case, the generator. So it can also be used to pass on state. And here the important thing is our promise type, which is part of the machinery, it stores. Basically, we have the type of our coroutine, and it stores a pointer to the last yielded value. In line 7, I have a member for the last yielded value, and I actually can store a pointer here because of the question before. It will live long enough until I have consumed it, so I get away with a pointer. And the next thing is important is this yield value function, which also has a special name. The yield value function is basically what should I do in this coroutine that is associated with this promise type when I encounter a co-yield keyword. And what we in a plain generator do is, okay, we get a reference, and we say, okay, our least yielded value, we store the address of this reference. And then the other thing that is important is here the return value. It says, what shall happen with our coroutine? Should it resume and just run inside the coroutine, or should it go back to the outside? And in the plain generator, we say for each value, we store the value, but then we suspend the coroutine. It returns suspend always, because we want our consumer, our iterators on the outside, be able to see and to consume this value, and only when they're done, then the coroutine gets to continue with the next thing. So this is the behavior for the plain generator. You see most of it is omitted. You see at the bottom, that's always also another thing that you can specify is what happens at the beginning of the coroutine. So most coroutines are lazy. They are initially suspended, such that you don't run any coroutine code when you use the coroutine, because actually also for generator it is, if you call the function that returns the generator does not yet start running. It only starts running when you actually call begin. So that is for this. And now, if we want to move this to batched, the thing we have to do, the central thing we have to do is, we don't store a pointer to a single value, but in line 5, we store a buffer. I have a promise type, a batch promise type, which I will use for a batch generator. It is templated on the type I'm yielding and on the batch size in this case. There's ways to specify the batch size at runtime, but that is for now beyond the scope. And now our yield value has to do something different. We get some value. We push it into the buffer via perfect forwarding because we're good citizens. And then we have to return something that controls whether to suspend. And we don't want to always suspend. We also don't want to always continue. We want to suspend if and only if this last element filled our buffer to the capacity such that we want to yield it. And this is encoded in some type which I call suspend if, with the condition, is my buffer full? I'll quickly show you this. This is suspend if. This is also a thing that needs to have special member functions. This is so-called awaitable. So the important thing here is this in line 5, this await ready. This is basically the coroutine machinery asking the struct, do you immediately know if I can continue, or should I put myself to sleep in some way? And this says this awaitable is ready, so you can immediately continue if we should not suspend. So it's just the inverted thing here. That's why we negate or suspend variable. And that actually is the only thing we have to do, because the other things for await suspend, this is basically controlling the suspension. We don't have to do anything because the default behavior is fine here. And the line 12 is when we are coming back from suspending in this co-yield call, what should we do then? Also nothing special, just continue the coroutine where it was. The only thing that this does is deciding if we should suspend. And then what we have here is a basic, also greatly stripped of most of its internals, generator class. And the only thing that you have to need for now is that the generator, it has this special inner class promise type in line form, which has to be called promise underscore type, because that's where the compiler gets the behavior from. And what it of course also had, it shall be a generator, it shall be iteratable. It has some iterators, which then interact with the coroutine. I will not show you that because it's not important for what we're doing now. And it has an iterator which is begin and an end thing to compare with. And we don't have to do much, because now, as if you remembered, if we replace our promise type in line 4 from the plain generator promise by the batched generator promise, then we will get from our iterators, we will not get the value, but we will get batches of values. We'll have replaced our value by a vector, by a batch. So what we can do here is that the outer thing, the generator that does the iteration, again, basically does the join for us. What I have here, unfortunately, in line 25, it's a very, very long type because we cannot immediately instantiate this because at the construction time of this generator, we don't have access, but we store basically a join view of a range that stores our internal begin and end iterators to the batches, and we do a views join, so flatten in other languages over this. And then that is the easier part because it's not coroutine related. I just do at the begin. When I call begin, I have to first initialize my variable with the join view. I have to get my actual join iterators, and then I return the begin. And for end, you still have to check. I did put the in place join in both variants because it might be that there's people who put first the call to end and then the call to begin when they iterate over it. I don't know why anyone would do this, but it has to work. So we have in both places to engage our optional with the join view if we want to do this. So this thing, it just works and does the right thing if you add all the things that I have left out because slides are short. And if everything works, then why does this slide title say the Valley of Tears? The thing is, it works, but it is as slow as before because I do batching, and I know that I'm really assuming that the batching helps because I also saw my manual batching that gained me something. But apparently something in my generator internals that the compiler then transformed into something negated all my possible batching gains. Sad. When I first figured this out, I was really devastated. I thought, okay, it's not that long into the conference. I don't have a talk anymore. Let's see what I'm going to tell you instead. And I also had quite a lot of other things to do this month. So that the initial feeling was not great. Then I said, okay, you're not only like a programmer, you're also a scientist, an interested individual. Let's see what is going on there, if we can learn something and then have at least a learning moment, because learning moments are much nicer than moments of failure, I have to tell you. And what I found out, okay, in general, not only in this particular case, the code generation that the compiler does is not in general, let's say not only bad or improvable, but it's also very vulnerable. In particular, if you do some line which semantically makes no difference, if you put it before the co-yield or after the co-yield for those tiny examples with simple integer manipulation mechanisms, sometimes it changed the runtime by a factor of 2 or something, which is unexpected because for normal functions we are used that if we swap some lines in a way that semantically makes no difference, the compiler understands it, even our CPU understands it, and they will reorder it just in the right way and we don't have to care about it. But apparently for generators this is not the case, and this is inherently already bad because that is things that you can teach that you don't want to worry about, especially if it's so subtle. And then a thing on the higher level, we have a little bit of a problem of a chicken versus the egg, and that I mean there's us, the programmers, who say we don't use those coroutines because they are slow and the code generation is brittle. And then there's the compiler vendors who say nobody is using that. I spend my time improving other features and then it will never improve. That's an issue. Maybe it will get a little bit better with C++23 if we slowly get also library support, also with the senders and receivers in C++26 for things that use coroutines that people accidentally, because it's in the library, use it and then the compiler vendors get more feedback. Yeah, but that's then a more on the political level, something I found. Then I looked even more into detail. I wanted to ask, okay, if it's slow, I want to find out why it is slow. What does the compiler not understand? And if you look at this, I would suggest you to look at the comments of the right side. There's 2 types of instructions. So the first thing I have to say, this is not the disassembly of a thing of the Fibonacci view, but of a iota view that just increments the numbers just here to 1, 2, 3, 4, 5, 6, 7 because of the assembly becomes readable. And this is basically the loop inside the generator that does the vector filling until it is full. And here, so I wanted to get you have two types of instructions. The ones that you immediately see why you need them. I do some incremental of numbers, such I need to increment a number somewhere. Here in line 2, I add 1 to some counter, that is the current number. Sounds reasonable, we have to do this some way. Or also, we have to keep some iterator, we write into a vector, we have to know where in our vector we have to write. So this in line 8, we have a vector iterator, we increment it by 8, because 8 bytes is the size of a size t, then we need it. But then there's all those other things. Line 3 and line 4, and also line 9. Those are things where the compiler inserts, oh, I have this thing in a register, please also dump it into RAM. Which is say it's not super expensive, it's a write from a register into something that is probably hot in the L1 cache if I'm doing this all the time in a hot loop, but it's definitely not free. If you do 3 of them, in this kind of low-level scenario which we are, you can measure this, and this actually makes the difference. So, thank you. That is the problem. Now the point is to understand why does the compiler do this. And the reason is, it has to sometimes do this because if my coroutine suspends, then I have to do this. Then I have to say everything that my coroutine still needs after I've suspended. When I come back, then I have to remember my state from before. And this I have to store, in this case for coroutines, on the heap. That is perfectly valid, no way to get around it. But for some reason, the problem is here is that this is also done in the case where I'm not suspending. I have this, so the high-level reason is that the compiler does not understand my suspend if, that it says, if I don't want to suspend, then please don't spill my registers onto the heap. That's the issue. And even more subtle, you see that in line 15 I annotated, there's this code that stores, you remember this suspend if struct that decided on whether to suspend. It had a bool member. For technical reasons, it needed this. But this bool member, it is needed before the suspension to decide whether to suspend. But after the suspension, is never accessed. But the compiler also is not smart enough to figure out this and stores it nevertheless. What I then did to say, okay, let's do something a little bit more deep. Throughout, we have these nice tools called compiler explorers, and we have those nice tools called JetGPT that also understand assembly. Let's try to get rid of everything here, basically move all those register spilling manually by modifying the assembler to a place where we know that we suspend. So basically first do, if we are going to suspend, then do all the spilling. Then this is here. Basically, I removed everything that I don't need in the hot loop manually. So I basically wrote the thing that I expected the compiler to write. And then after this, what I omitted way, I still have those writes to RAM, but not in every iteration, but only if we are actually going to suspend. So now here we have a hot loop, and the hot loop does nothing that it does not absolutely necessarily have to do. I did something else. There were 2 checks. Basically, is my vector full at capacity, and is my vector full at the batch size? These are redundant because both are the same. We could help the compiler by using better code, but I still removed it to just see where we can get. Yeah, that is at least at that point I figured I had something, an interesting story to tell at this point. And also it was faster. For the simple example, I got 50% of this hot loop out because I basically also removed 50% of the instructions. Instructions are not equally expensive, but still that was my measurement. And then also the thing is, to make coroutines good, compilers need to learn this. So register spilling is expensive. Only do it if you're actually going to suspend, because then you really are going to need it. Otherwise, it might be that you stay a while in your coroutine. And the other thing they need to learn is this heap allocation elision, that it just says, oh, I know this. This is a complex coroutine, but it just does the Fibonacci numbers. Those are 2 integers. I store those 2 integers on the stack, do the addition there, and get rid of everything that this coroutine is. That is the second part. And that is what's missing to make them really even more usable and more consistent. So, getting towards the end, I'm still convinced that std generator or coroutines in general or other modified generators are a very useful tool, especially if you can afford the overhead, but you have complex logic to do that is much more maintainable than using, for example, manually written iterators with all that boilerplate. But it definitely has some performance issues. It is not a zero overhead abstraction because I could do something which is equivalent and is much faster. And the thing is, if we maybe are nice to our compiler vendors, maybe something will happen over time. Let's see. We need Halo. We need better code generation for the internal state machine generation of the coroutines. I've also, like, last night when I could not sleep, looked a little bit, say, ChatGPT, explain me where does this happen in the coroutines.cc of GCC 14, but that's a time for another talk. Let's see how hard it is. And also, as I said, I gave you 2 slides about roughly skipped internals of these generators. And if you want to get into coroutines, then generators are a good starting point because you have them in the standard library of high-quality implementations. You can just read on what is going there, what are these internals, how do they interact. And they're not too complex, so not too complex for a coroutine, to say, because they are synchronous. You don't have, like with all these asynchronous stuff, you don't have like anything scheduling stuff, but I have my values. Once I'm done with my values, I get back to the iterator, and once the iterator advances, I get back to the coroutine. So it's one of the simplest useful coroutines that you can write, so it's a good point to start. This finishes my presentations. I think I have something like 2.5 minutes, so we can put a round of questions. Yeah.